Okay, first application is chemical mixing problem. This is in um, sorry, section 3.2. So compartmental analysis. So compartmental means that uh, we, um the we can break it down to complicate system into multiple simple systems. So for example, when you think about the car. Okay, so here's maybe this car right here. And then there is a brake system right here. Maybe here brake system. So, and here's actually the dynamic system is the engine part. Let's just say engine. Okay. And then in the here engine there is the fluid system. There's a dynamic in the fluid system maybe right there. Okay. Okay, this is the example. So there are so many systems uh, the applied in the car, and then that complicate systems the working together to operate the car, right? So that kind of this one kind of the things that consist of the multiple systems is called compartment. Okay, so we're gonna break to analysis or to figure out the system how that works. We're gonna break down the this set of the systems complicated into the single systems, and then we're gonna take a look at each systems. So that's a strategy. So likewise, in chemical mixing problems, what are you gonna do? We want to figure out, let's say here, okay. Think about, here's a tank, maybe water tank or something liquid in it, and then there is an input. Water comes in, and the water comes out. Okay, so there's okay, here's initially this much of the liquid in the tank. And then this is not the pure water or pure liquid. There is some substance here. That is called, let's say this is X of T. Since the liquid comes in and the liquid comes out, the amount of substance will be changed at time T, right? So we want to figure out the mass of that substance, X of T. So here, let me see, this is maybe input rate right there. Input rate means yeah, input rate of the substance, and then this is output rate of the substance. Okay. So here X of T to represent the amount of the substance in the box, in the tank, whatever. Okay, at time T. Time T. So we assume that the X of T is not spontaneously forming, reacting, so that it will becomes to the substance, okay, and or disappearing. We will assume that it's not gonna happen in such a case, such a cases. So here, what kind of you to figure out x of t, we need to adopt the physical law. That is the conservation principle. Conservation principle says that in chemical, sorry, this is the problem number one, chemical mixing problem. Sorry, I should have noticed this. Chemical mixing problem. Okay. So dx dt. Okay, so that's the rate of change. Infinitesimal rate of change of the substance must be equal to the input uh, mass of the substance, mass flow rate minus output mass flow then rate flow rate. Yep. Okay. So what does that mean? Dx dt is equal to this, but dx dt, yeah, at the moment, it means that at the moment, the rate of change, the change of x of t must be constant. That's the meaning of a conservation principle at the moment. Okay, so it should have a uniform difference between two rates at the moment. Okay, so we're gonna use this one, the conservation principle, to build up the differential equation to figure out the x of t. Okay, so keep in mind this to model the something, physical phenomenon or natural phenomenon as a differential equations, always start from the physical law. Okay, we just observe the natural phenomenon or physical phenomenons. Okay, and then we in physics we're gonna model that phenomenons using mathematical tool. Then most of cases, I think 99%, it becomes a differential equations. And then we want to solve this differential equation to figure out the solution so that we can expect or understand the behavior of the phenomenon. Okay, that's the whole process. So here's okay. So to build up the differential equation from the conservation principle, I'm gonna introduce the unit. First, I think we need to figure out the unit first. So introduction to unit. So first one, volume. Yeah, so input rate is, yeah, so a certain amount of liquid comes in. So this is liquid. It should have volume, right? Volume for flow rate. The unit for this one, the unit is the volume. Normally liter, right? The liter over time. The second one, concentration. Unit is the mass over mass of substance, okay, over volume. So how many mass the substance merged into the volume, into the amount of the liquid? That's a concentration. And the three is mass and flow, the rate. So this unit gonna be mass over time. Okay. So here, mass means the substance, okay? Yeah. So let me change this one to this pen. I think this is better, right? So then the mass flow rate can be the mass flow rate. Is it? I think it's the same. Let me change it. I think this is better. Mass flow rate then can be computed by computed by what? Volume flow rate times concentration. It makes sense, right? So how many mass in the liquid? Then we need to multiply the amount of the liquid times concentration of the substance, right? So volume flow rate times concentration. That's how to calculate the mass flow rate. I mean, similarly, what? If you when you want to find out mass flow out, the mass flow rate out, or so we compute the mass flow rate out times concentration out, right? So anyway, so we're gonna apply the unit for each terms in this formula. So volume flow rate gonna be liter over minute, for example. This is the example, okay? And then times what? The concentration is a mass over volume. That's the unit, right? So let me use a kilogram over liter. Okay, this is equal to. So see, the liter and the liter cancel them out. So we got what? Kilogram over minute, right? Over minute. It makes sense. What's the unit of mass? The mass over time. You see, we got the mass over time. Kilogram over minute. Okay, that's true. Okay. So normally we use a liter for volume, and then minute for a time, and then kilogram for the mass. But not always. Okay. So see example. This is the example one in the textbook. Okay. So okay, so this is example one textbook. Okay, so basically the problem says that the 1,000 liter pure water, okay, in the tank right here, okay, in a brine solution, I mean, okay, it's a solution right there, and the 6 liter per minute is comes into tank. It's a brine solution with 0.1 kilogram per liter concentration, and the 6 liter per minute, which is exactly same amount of the flow rate in, is comes out. So we need to find out x of t. Okay, so then x of t is the mass of salt. The problem says that the x of t is the mass of salt in the tank at time t. Okay, so and then next one, the volume, flow rate in is 6 liter per minute. Okay, and the third one, and the volume flow rate out is the same amount as the rate in. And the concentration of salt is 0.1 kilogram per liter. Okay, so now what are you gonna do? We so put them into the conservation principle. Okay, so applying the conservation principle, then we get this dx dt. Okay, dx of t actually, but let me skip writing parenthesis t. Dx dt is equal to input rate, or we can say input mass flow rate, okay, minus output. Yep, output rate. And let's figure out the input rate and output rate. Okay, so first one, input rate, input flow rate is gonna be what? Input volume of water flow rate, right? It's gonna be input volume of water flow rate times what? Times concentration, right? Of salt in the brine solution by entering the tank. Okay, so yeah, simply input volume of water flow rate is 6, right? 6 liter per minute, right? Times what? This concentration is given, right? Which is 0.1 kilogram per liter. Yeah. So let me skip writing the unit. So we got simply 0.6. Okay. Next one, output flow rate. Okay, output flow rate is going to be, yeah, then output volume of water flow rate, which is 6, right? 6 liter per minute times concentration of salt in the brine, not entering, right? But just leaving the tank or accumulating the tank. What's that? What's the concentration of salt that coming out from the tank? Anyone can figure out this? This part, the concentration of salt come. Hmm? Yeah. X of T over 1000, right? Then yeah, kilogram, yeah, so kilogram per liter, yeah. Because this is X, because also unit of the concentration, the mass over a volume, right? So here mass of salt is X of T, which is the exactly same as mass in the tank over 1000. So that's gonna be then 3 over 500 times X of T. Yeah, thus dx dt is equal to 0.6 minus 3x over 500. Okay, so this is a linear equation, actually. I mean, this is initial value problems, and then this is linear equation. Or you can use either linear method of integrating factor or separable. You can say this is separable too, right? Either one just fine. Yeah. Mm, yeah, let's solve it. So let me use the method of separable. Okay. So first one, I'll set this is the function of x. All right. So I'll move this one to the left-hand side, and then I'll move dt to the right-hand side to separate the tx terms and t terms. So we got this then 1 over, okay, 0.6 minus 3x over 500. The dx is equal to dt. I'm using the method of separable, okay, considering this equation is separable. You can apply the method of integrated factor because this is linear. Either one just fine. So now then yeah, simplify the fraction. This is a fraction of a fraction, right? So simplifying the fractions, we're gonna get 500, right, over and a 300 minus 3x dx is equal to dt, right? And then, well, guess what? I'll just uh, uh, in this case, 500 over 3 is kind of common factor. So I'm going to factor out. So 500 over 3 times 1 over, 100 minus x, the dx is equal to dt. Now we take the integral. Okay, 503, just take out integral. The 1 over 100 minus x dx is equal to integral dt, right? Okay. So what's the integral to this, the fraction? Integral to this guy is literal, right? And the actual value, 100, isn't it? And then we put the negative sign right here, 100 and minus x. Okay, this is equal to t plus, let me say c1. Okay. And then I think there is assumption about the this one, so that I think this is positive, isn't it? Yeah. It should have something about the some condition, so that absolute value 100 minus x, 100 over minus x is always positive. I forgot the problems, but I think there is something mentioned about that. So then we got the natural log, and then 100 minus x is equal to minus t. Okay. Oh, we just move minus 503 on the right hand side, so we got minus 3 over 5, 3 over minus 3 over 500 and t, and then plus c1. Oh, c2, sorry. Here c2 is equal to minus 3 over 500 c1. Sorry. So now then 100, and then what? 100 over minus x is equal to e to d minus 3 over 500, right? And then t plus c2. So x is equal to, well, x is equal to 100, right? And then minus e to d minus 3 over 500, and a t, and a plus c2. This is equal to 100. I'll just decompose that exponential term. 100 and then minus c3. Now you know what c3 is, right? Minus 3 over 500 and t. Okay. And here c3 is what? E to d c2. Okay. Now let's figure out c3. That's a constant integration, can be determined by initial condition. So since the x of 0 was 0, right? So, but let me plug in 0 into t in the general solution. This is general solution, right? That's the general solution. Oh, not this one, sorry. Here, this is general solution. Okay. General solution right here. X of 0 is 100, right? And then minus C3. Because e to the 0 is 1. And then that must be equal to what? That must be equal to 0. So C3 must be equal to 100, right? Okay. So the initial amount of the salt is 100 kilogram. Okay. Now then, okay, we got particular solution. X of t thus x of t is equal to 100 minus e to d negative 3 over 500 and the times t. Oh, I forgot putting 100, okay? This one. So which means that what? Taking out 100, because this is a common factor, so we got minus 1 minus e to the minus 3 over 500 and the times t. That's it. And then you can see that here, what? As t goes to infinity, then x of t approaches 100, right? X of t as t approach infinity is equal to 100, because this is exponentially decreasing. So it makes sense, right? Yeah, that makes sense because in there here, you see, water comes in with that concentration over and over, then you know the mass of that substance, mass of the salt becomes the what, initial value, which is 100. Right? Okay, so I think all right. So what are you gonna do? Now we need to find out. This is just additional. I just curious that what happens at t equals infinity. Sometimes, yeah, we need to figure out the behavioral solution. So once we find that x of t, yeah, okay, that's the answer, okay. But I just wanted to figure out what happened t approaches infinity. What happened t approaches negative infinity? What does graph of x of t look like? Sometimes I'm just curious, and then maybe you need to figure out that. So that's what I did. And the second question is to figure out the concentration of salt in the tank at time t, right? So the concentration of salt in the tank at time t. Okay, at time t is what? Oh, just x of t over 1,000, isn't it? Okay, so this is equal to 0.1, and then the 1 minus e to the minus 3t over 500 kilogram per liter. Yeah. So the second question, I think, to find out I think I forgot the question in the example one. We need to find out, hold on a second. Mm, yeah, find the time t when the concentration of salt becomes 0.05. I think that's the question, the problem. So to find out the time when the concentration reached 0.05, we set what? We just set 0.1 times 1 minus e to the negative 3t over 500 is equal to 0.05. Okay, we just set this. Okay, and then solve this equation for time t. Okay. Yeah, let's do that. So we got this e to the negative 3t over 500 is equal to 0.5, right? Because divide by 0.1 and then subtracting subtracting 1 and then change the sign. So you got this. Okay. So now then negative 3t over 500, just take a natural log on both sides. So we got natural log 0.5 on the right hand side. And then isolating t is going to be negative 500 over 3 times natural log 0.5. Okay, so this is approximately uh 115.52 minutes. So it will take this time 115.52 minutes to reach 0.05, the concentration. Okay. So that's the example one. And then example two is the similar to example one, but the only things that the difference is that the volume for rate in is different from the volume from rate out. So here's x of t. I mean, maybe x of t right here. And then initially 1,000 liter in the tank. And it comes in is, I think, I just forgot this, I don't know, let's say just a liter per minute. Okay. And then this is b liter per minute. Okay. Hold on a second. What's the problem? Uh, Yeah. So A and B, okay. Think about this. If A is different from B, I mean, I mean, let's say A is greater than B. A is greater than B. Then what happens? If A is greater than B, and let's say AB, here C kilogram per liter. That's the concentration of the volume comes in. Okay. So if A equals B, then the what? The amount of the water or liquid in the tank will be increased because A is greater. The amount of water comes in is greater than the amount of water comes out. That's what that means. A is greater than B. That means that the amount of water or liquid in tank is increased. Then what? Then dx over dt is equal to B times, oh, sorry, A times C. That's the what? The what input rate in, right? Input rate in minus, and then B times concentration is not just x over 1,000, x over 1,000 what? Plus what? A minus B, right? Times T, isn't it? Okay, if you just if you generalize more, let's say this is the alpha, then we're gonna get alpha plus A minus B times T. That's the bottom. So this is the concentration of the salt comes out or in the tank. Concentration of substance in the tank. Okay, so keep in mind this. Um, okay, that's for the 3.2 chemical mixing problem. It was just simple example in about the compartmental system. Now in I think chapter 5, we're gonna study two systems coupled. So we're gonna see this kind of problems when you learn the system of differential equations. Something comes in, comes out, and then that one comes in another system, and it comes out. So two systems couple, so we're gonna get the two differential equations. That's a system of differential equations. Okay, so we're gonna learn this one in chapter 5, but anyway, that's for the chemical mixing problems, an example, simple example of compartment system.